Hi, I'm Dane Quinn from the University of Akron, and today's video lecture I'd like to discuss some of the characteristics of common kinematic mechanisms that we're talking about in this class, in particular slider cranks and 4-bar linkages. So we'll start off with the slider crank. Here I've kind of showed the most general version that I can come up with. It's an inclined offset slider crank and driven by what we're calling link 2. So here within this, the inclined part of this description means that the direction of the slider motion is not horizontal, right? So you can see that it's inclined. It's offset so that the direction of that motion does not pass through this rotation of link 2. And here, link 2 is represented by this sort of strange blob shape. Now, really, what's important is the constraint that link 2, this object is pinned at O2, and then the connecting link is pinned at A. So you could think about putting in just a rigid link between O2 and A, and we would have a common sort of familiar configuration. So with this, right, let's go through and define some directions, right? So let's define, of course, I and J as fixed in the ground. And then I'm going to identify I2 and J2 fixed in link 2, and I2 will be in the direction of A with respect to O2, right? So that's I2, and then J2 will be perpendicular to that, with the angle theta 2 describing that rotation. Notice here, theta 2 is given, it looks like it's about 120 degrees or so from horizontal. And then we'll take I3 and J3 to be in the direction of link 3. Right? So that's going to be I3 and J3, of course, with the angle theta 3. And finally, I am going to identify the direction of the slider motion. And so I'll call that E1 and E2. Right? So here, E2 is parallel to the motion of the slider. And we'll define the angle psi that relates E1 and E2 back to I and J. Notice that E1 and E2 are actually Cartesian because they're fixed. They don't change as this mechanism moves around. That's in contrast to I2 and J2, which definitely change their orientation with respect to I and J as this mechanism moves. Right? So E1 and E2 are basically fixed directions. They're just not horizontal and vertical like I and J are. Now, our loop closure equation looks like, let's see, let's go and kind of represent that. So we would have a vector from O2 to A plus the vector from A to, say, B, and that equals the vector from O2 to B. Because of this sliding constraint and the fact that the offset is constant, the position of B with respect to O2 can also be written naturally in terms of the E1 and E2 directions as a component in the E1 direction that happens to be fixed, and then a component in the E2 direction that can change its magnitude. So here we see that we need an additional coordinate to describe the displacement of the slider. And we'll define that as x. So our loop closure equation can be written as R of B with respect to O2 is R of A with respect to O2 plus R of B with respect to A. So now using these links and directions and coordinates that we've defined, the position of B with respect to O2 can be written as D in the E1 direction plus X in the E2 direction. And over on this other side, we'll write this as L2 in the I2 direction plus L3 in the I3 direction. So notice that in blue, we have a good loop closure equation. It's a vector equation, so it has two scalar components. Notice that D is known, E1 and E2 are known, right, because these directions are fixed. X is unknown. So actually, I'll go and color that red. I2 is variable, but it's known. It's our input angle. We'll make that green. And then finally, I3 is an unknown direction. So here we have two equations, two scalar equations that will come out of this, and two unknowns. We do need to relate these directions, right? So I2 is cosine of theta 2 in the I direction plus sine of theta 2 in the j direction. Remember that theta 2 here is a fairly large angle, but cosine of 120 would actually be negative, and sine of 120 is positive, so I2 for theta 2 equals 120 points in the second quadrant. And then j2 is minus sine I plus cosine theta 2j, and that works out, again, if theta 2 is 120 degrees, like shown. I3 and J3 are similar, cosine I and sine of j. J3 is minus sine of theta 3 in the I direction and cosine of theta 3 in the j direction. Finally, we need these Cartesian directions, E1 and E2. So here, E1 is equal to cosine of psi. Remember, this angle psi is fixed, minus sine of psi in the j direction. And E2 is sine of psi in the I direction and cosine in the j direction. So here we have all these directions written in terms of I and j. And if I want to solve, for example, for the slider displacement, so say we want to solve for x. Well, the easiest way to do that is to eliminate the other unwanted unknown, right? So if I want to solve for x, that really means that I want to eliminate theta 3. And the easiest way to eliminate a direction is to solve for a magnitude. So we'll isolate this term. All right, so we'll say L3 I3 is equal to D E1 and X E2 minus L2 I2. So notice that we have isolated this term L3 I3, which contains the unknown that we'd like to eliminate, theta 3. And now we'll just take the magnitude squared. Right? So we'll take the magnitude squared of the left-hand side and the right-hand side. And the best way to do that, the easiest way to do that, is just to dot each side with itself. Right? So this term on the left becomes L3 squared. Here, and you can work these out, you end up with d squared plus x squared. And then when I dot this term and the L2 I2, I get a minus 2 d L2. And then I have E1 dot I2. I also have to dot x E2 with L2 I2. And I get 2x L2 E2 dot I2. And then plus L2 squared. This might be a good time to pause the video and go through and work out this on your own. Right, so you're taking the dot product of the left-hand side with itself. That one's pretty easy. That gives you L3 squared. But then when you dot the right-hand side with itself, right, you get this expression here. And this reduces then to L3 squared equals d squared plus x squared. And then E1 dot I2 is cosine of psi, cosine of theta 2, minus sine of psi, sine of theta 2. Remember, psi is the angle of the direction of the slider. We have 2xl2, e2 dot I2. Well, that's sine of psi, cosine theta 2, plus cosine of psi, sine of theta 2. And then we have an L2 squared. Right? So if you notice, this equation in blue that we ended up with just contains the unknown that we're interested in, which in this case is x. Right? X is here. So we have an x squared there. And then x is over here as well. This equation is just quadratic in x. Quadratic formula, right? We solve because everything else we know. We know the lengths, the d's and the L2s and the L3s. Psi is this angle, which is known. Theta 2 is the input angle of the driving link. So that's assumed to be known. And then, again, we just have x. So this general inclined offset slider crank, right, to solve for the position of the slider, right, it's a very similar procedure to what we would go through if we had just kind of a, I don't know, a regular slider crank that was not inclined and not offset. I will point out that continuous rotation of link 2 so that's the input link. So in order for this input link to make a complete rotation, it requires a little bit of geometry. And in particular, it requires that L3 is greater than D plus L2, really greater than or equal to. Right? So if L3 is not long enough, then when link 2 is sort of opposite of this offset, then it can't connect down. Right? So basically link 3 has to be sufficiently long in this case so that link 2 can make complete rotations. And if it is, then this slider basically stays to one side or the other, depending on where it started with. So this is a constraint of sort of properly designed mechanisms, at least mechanisms that are designed to undergo complete rotations by the driving link. So a little bit more about slider cranks. So inversions are obtained by grounding different links. So here in this large picture, I have, again, a slider crank. I have this slotted link, right, which you can think about the slider, and I have a shorter link and a longer link. So depending on which one of these links I fixed to the ground, I can get basically different configurations, different kinds of mechanisms. Right? So here, if I take and I ground this dark gray link, I get back to the traditional slider crank. Right? So this looks like just a slider sliding in a slot. And I've kind of grayed out the grounded link here. Now, in contrast, if I were to ground, so let's call this link 2. Let's call this link 3. And because this thing may or may not be able to move, right, I'm going to refer to this as link 4. So if I ground link 4, I get a slider crank. Right? If I ground link 2, I get a mechanism like this. So the slider can actually be represented as a collar that slides on link 4 as these things move around. Then if I ground link 3, right, I get actually a similar kind of mechanism. Right? So here maybe you have an actuator that pushes back on this point, and as this actuator changes its link, it rotates what would be link 2. And as a result, this also changes its direction, right? So link 4 here would kind of rotate back and forth. Finally, if I ground the slider itself, we actually have a mechanism like this, right? So link 2 and 3 would change their orientation, and then this dark gray link would move back and forth, left and right, through this grounded collar. Right, so if I look at the link loop closure equations for these links, right, so let's set some directions up, right? So we'll set I2 and J2 along link 2, right? We'll set I3 and J3 along link 3. And then finally, we'll define I4 and J4 to be fixed in link 4. So now our loop closure equation is the following. The vector from here to here plus the vector from here to here equals the vector from here to here. Finally, we recognize that the length of this vector can change, right? So we'll need a coordinate that describes that. Right, so let's call that Z. So looking at this closed loop, we see that L2, I2, plus L3, I3 equals Z, I4. And again, at this point, none of these are necessarily grounded, right? So we have really 4 unknowns and 2 equations. We have too much information here. Or we have too many unknowns. So if I start to ground one of these links, then I actually get loop closure equations that can be solved as 1 degree of freedom systems. So over here, basically, I4 would be grounded, right? So I4 would be known. In this case, it would be just a fixed direction, right? So my loop closure equation would look like L2, I2, plus L3, I3 equals Z, and then I4. In contrast, over down on the lower left, here, I2 would be known. So looking at this loop closure equation, actually I'll just take this one, I'll copy it. Again, this is the loop closure equation, but now I2 is a known direction. So we have three variables: the direction of link 3, the direction of link 4, and the distance. We would choose one of them and solve for the other 2. Looking at this mechanism, or this configuration, again, back to same loop closure equation, but now theta 3 is known, so that I3 is a known direction. Again, 3 variables, choose one, solve for the other 2. Finally, for this last inversion, I4 is known, and let's color that blue. So we have 3 variables. Choose one, solve for the other 2. It's interesting that the loop closure equation for this mechanism and this mechanism, it's exactly the same. And the loop closure equation for these 2 are very similar. The only difference is which direction is unknown, right? So here, the known direction is I3. Back over here, the known direction is I4. But by grounding different parts of this mechanism, right, we get different inversions of the same fundamental linkage. So now let's look at 4-bar links, 4-bar linkages. We actually have a nice way of thinking about the solution to these geometrically, right? So here I've kind of shown a 4-bar linkage disconnected, right? So this is going to be link 2. Link 1 is the ground, and this is link 4. And then finally, I've shown link 3 kind of in 3 different configurations, right? Over here, I've connected link 3 to the end of link 2 and just kind of put it in a random spot. Over here, I've connected link 3 to link 4 and put it in 2 different configurations. Now, the proper solution for this linkage is to bring this blue connection over to the end of link 2, right? So let's say that this is point A, and I have 2 different configurations depending on where link 3 and link 4 are. I've kind of got A prime and A double prime, right? These, in a connected mechanism, all occupy the same spot, right? So how do I bring this point over to this point? Likewise, I have B prime and B double prime over here, and these 2 points would be connected, right? So you can maybe kind of see how this works, this sort of geometric solution. If link 2 is known, then the end of link 3 has to be a fixed distance away from A, right? So that's going to essentially trace out an arc, right? If I were to look at all different paths that B prime could occupy. Now, in addition, B also has to be a fixed distance away from, well, let's call this O4 and O2. So that's going to lie somewhere on this dashed circle. Well, the only place these 2 things meet is right here. So finally, the only way that I can connect this yellow dot and that yellow dot and that blue dot and that blue dot is to have link 4 here and link 3 connecting them. So this would be the configuration of this mechanism when link 2 is oriented as shown. This is kind of a geometric construction for the configuration of the linkages. And you can do this really for just about any linkage. If you wanted to figure out what these angles are, well, if you draw this accurately enough, right, you could actually go and measure all this stuff out. So now one question is, again, continuous rotation of the input link. Well, so this dashed line represents the path of point A, assuming that it undergoes a complete revolution. So now, in this shaded region that I've shown, that's basically all the possible locations of A when I connect 3 and 4 together. So you can kind of see that this inner circle would be reached if 3 and 4 are parallel but kind of opposite orientation, while this outer circle would be reached by 3 and 4 completely stretched out. So anything within these 2, this annulus, I can reach with the end of link 3. So as long as this dashed line is inside this annulus, link 2 can make complete rotations. Right? So what does that imply? Well, it means that if I look at, say, this right edge of where link 2 could be, that means L2 has to be less than or equal to, well, L1 plus L4 minus L3. So that would be looking at this point, this sort of extreme point of link 2. Now if I look at the point on the left side, that means that minus L2 has to be greater than or equal to L1, so all the way over here, minus L4, so that would be link 4 stretched to the left, minus L3. So these are our two conditions. And rearranging these, we get L2 plus L3 less than or equal to L1 plus L4. And this second condition looks like L3 plus L4 greater than or equal to L1 plus L2. So it turns out that we can combine all of these things for all the different designs and configurations of a 4-bar linkage into what's known as Grashoff's condition. So if we order the links from shortest to longest, right? So L shortest, L intermediate, 1 and 2, and then L longest, then if the sum of the shortest and longest links is less than the sum of the two intermediate links, then the shortest link can undergo complete rotations. So here, for this mechanism, that implies that the sum of link 2 and link 3, those are the two shortest links, is less than or equal to the sum of link 1 and link 4, those are the intermediate links in this case, then link 2 can undergo a complete rotation. Well, that's just this condition that we came up with originally. And so it turns out that this condition implies this second one, right? As long as this is met, then this mechanism can undergo complete rotations. Now, if, say, you had a configuration or you had a linkage with 4 being the longest, right? Or maybe 2 being the longest, or some other ordering, Grashoff's condition always works as long as you identify the shortest and longest links. So now we can generate inversions for 4-bar linkages as well. So here we have 4-bar linkage, and I'll let theta be the angle between this link, which we normally think about as, say, link 2, and maybe this link below. And again, looking at the loop closure equation, we're going to define I2 and J2 fixed in this link, I3 and J3 fixed in this link, I4 and J4 will be fixed in this link over on the right. And then finally this I will define with I1 and J1. Kind of thinking about that is what would be, as seen over here on the right, the ground link. So the loop closure equation in this case is L2 I2 plus L3 I3 equals L1 I1 plus L4 I4. Or, kind of drawn out, this vector plus this vector equals this vector plus this vector. All right, so here this is L2, this is length L3, this is length L1, and length L4. So what I've shown here are the different inversions. And in particular, I have traced out the path of the free connections in each inversion. So just like before, we'll write out the loop closure equation for each one of these. Here, it's I1 that is known. All right, so this is the known direction. And then we have 3 variable directions. Choose one, solve for the other 2. So again, as theta makes complete rotations in this case, this point traces out this path, and this point traces out along this dashed line. I've shown limit positions. Well, I've shown one limit position in this configuration where links 2 and 3 are parallel, and that's the maximum angle for, well, in this case, actually the minimum angle for link 4. Now, in contrast, if I ground link 2, right, so link 2 will be fixed, because that means I2 is known. Then we get a mechanism like this. This is actually known as a double rocker mechanism. And notice that links 1 and 3 make complete rotations, and link 4 kind of goes along for the ride. Then, if I ground a different link, in this case, I will ground link 3. So I3 is known. My loop closure equation looks very similar, except now I3 is known, 2, 1, and 4 are variable directions. This is also a 4-bar crank rocker mechanism, right? So here link 2, if that's considered to be the input, notice that as this angle theta undergoes complete rotation, link 2 undergoes a complete rotation, link 4 rocks back and forth. These two are again very similar, just with different grounded links. Here I've shown the other limit position, right, where link 2 goes off to the left, and then link 1 comes back to the right. Right, so these are kind of folded back on one another, and that gives an extreme position for link 4. And then finally, last but not least, we have a mechanism where we have grounded link 4. Right, so now I4 is known. And again, I've traced out the paths of these free links, or these free connection points. This is a double rocker mechanism. So as this angle undergoes a complete rotation, we see that links 1 and 3 both rock back and forth. Right? So that's why it's called a double rocker mechanism. So again, depending on which link we choose to ground, we can get different inversions of the same mechanism. And these are all different useful mechanisms, right? Useful configurations. And the fundamental kinematics for each one of these they're very similar, right? Because they're all basically made from the same closed kinematic chain. It's just a question of which one we fix into the ground. Right, so that's a little bit about slider cranks and 4-bar linkages, some of their characteristics. and the different inversions that can be obtained from each kind of mechanism. So that's it for today. Thanks for coming, and I will talk to you again. No dog bloopers today, interestingly enough. Bye.